Welcome back to part 2 on locks. In the first part, we discussed multiple reasons why synchronization is required for multi-threaded programs. We also started looking into how we could actually solve those problems just in like naive approaches with some if statements, some variables like flags and stuff like that, and notes as well. And then we started to get the understanding of how locks work by allowing us to surround critical regions of code with these two lock and unlock statements, which allowed that critical section to be executed as like an atomic instruction. And these atomic instructions were instructions that were basically processed in one go without being interrupted, as if they occurred at one single time step. So this, in part 2, we're going to be looking at continuing on with multiple different types of locks, as well as that test and set instruction that we realized that we required. Cool. So the test and set instruction, otherwise known as the atomic exchange. Now, like we briefly discussed in part A or part 1, this is an instruction which is required to support the creation of simple locks. And what this says is we have a test and set method or function that returns an integer. It takes in a pointer and another integer. So what it does is it sets some integer variable equal to old. It sets some integer variable called old equal to the value of the pointer variable that it takes in. So it's basically setting this old variable to be whatever the value of pointer is. It eventually returns that old value, but before that, it sets the pointer value equal to new. Okay, so it's basically updating our pointer value, but it's returning the previous pointer value, if that makes sense. So it's returning the old value. So the way it works is that the calling process obtains the lock if the old value was 0. Otherwise, it does that spinning while it's waiting to acquire the lock. And no other process may begin another test and set until the first process's test and set is finished, because this is an atomic instruction. So how it looks in terms of our simple lock that we were working with is as such. So we have the same setup. We have a lock structure which just has an integer variable called flag. We say lock flag equal to 0, basically indicating that 0 means that the lock is available, 1 is that the lock is held, so it's all the same as before. And the unlock is basically the same as before. The only thing that changes now is our lock function. So what this says is while test and set is equal to 1, we're going to spin and wait. So that means that while a lock is currently held by someone else, I'm just going to wait. Now, in order for this approach to work correctly, on a single processor, it requires a preemptive scheduler, meaning that the scheduler can take a process out of the CPU before it requests it or gives the CPU up. But this approach also works on multiprocessor machines. So just a quick example, hypothetically say that the lock is not currently held. Okay, so what ends up happening? So our flag variable is currently 0. Okay, we'll come into here. So this lock flag address will basically be a pointer to this one here, which will be 0. And if we go inside here, so this will say old is equal to 0. Okay, it's going to update that 0 value to equal to the new one. And what is the new one that we changed? Sorry, I went the wrong way. Well, it's going to be 1. So pointer is now going to be have a value of 1, and it's going to return old, which was 0. So it's going to come here to while 0 is equal to 1, which is false. So this is going to basically finish, and it's going to return. Okay. But what we've done in that time is basically updated the flag to be 1 anyway, all within this function. Because remember, it's updating the pointer to equal new, and new was 1. So that's hypothetically if the lock isn't currently held. What if the lock is held? So we'll come into here, and this will say 1. This will basically be the value 1, right? Or this will be a pointer to the value 1. And we're going to say comma 1 equals 1. So it's going to come into here. It's going to say old is equal to 1. It's going to return the value 1. And it's going to say pointer is equal to new, which is also 1. So the pointer value is basically not going to change. Okay, so now we're going to have a case of where it returns the value 1. That's equal to 1. And all we're going to do is loop here until this changes, right? If it doesn't change, well, this will just be 1 again, and it'll just carry on waiting. So that's how this simple spin lock works using test and set. Okay, so it's pretty simple, but it does definitely work. So let's think about evaluating it. Is it correct? Well, yes. The spin lock only allows a single thread to enter that critical section, right? Only when the flag is set to 0 will it ever go inside, or will the lock function ever return and allow you to get into the critical section. Is it fair? Well, no. So the spin locks don't provide any fairness guarantees, right? Indeed, a thread spinning may spin forever, right? If the thread that currently holds the lock basically never releases it, that's a case where the other thread will spin forever. Or other threads might acquire the lock instead of an unlucky thread, and therefore it might spin forever as well. Now, in terms of its performance, well, in the single CPU, performance overheads can be quite painful. This would be quite painful. But if the number of threads roughly equals the number of CPUs, spin locks work reasonably well. So the idea here is that, well, if you can run more threads at the same time, it's not too bad to have multiple threads waiting as well. So in terms of it scores well in correctness, poorly in fairness, and averagely in performance. Cool. So that was one way of implementing a lock using a spin lock with test and set. Another is called compare and swap. So the idea here is that we test whether the value at the address pointer is equal to an expected value. Now, if it is equal to that expected value, update the memory location pointer to by pointer with the new value. In either case, return the actual value at the memory location. So the idea here is that if this value that we get from our pointer is equal to the expected value, then we update our pointer to equal new, and then we just always return the actual value. So what does this mean? So how does this change our compare and swap? Our lock. Basically, we swap out test and set, and we put compare and swap. So this is what it looks like now. So say our flag value was 0, and we expected 0. So in that case, our actual value will equal 0. Okay, so actual will equal this value here of this pointer, which was 0, hypothetically. And because actual is equal to expected, okay, so 0 equals 0, because we expected the value to be 0, and our actual value was 0, so this is cool. We then update the pointer value to equal new, which is 1, and we return actual. Okay, so this will return 0. 0 is not equal to 1, so the lock will return. So what does this mean? Well, if the actual value was a 0 and we expected it to be 0, meaning we expected it to be available, we expected the lock to be available and not held so that we could acquire it, well, then what we do is basically we acquire it by changing the pointer value to equal 1, which we do here, okay, and we return 0, indicating that this will be false, so we can actually exit this function, and that's how we acquire our lock. Now, hypothetically, if we expect it to be 0, indicating that we kind of want it to be 0, meaning that we want to acquire the lock, and if it is not, if our actual value is 1, well, what we'll get is we'll say 1, actual is equal to 1. We're going to return 1, and that means we're going to have 1 equal to 1 here, which means that we're going to spin all the time. So this is how compare and swap works. Basically the same as test and set, but in a slightly different way. Now, another approach is to utilize what we call loaded link. This is sometimes LL, and store conditional, which was SC. You'll sometimes see it written in that sense. And this changes a few things. We add in a couple more functions. So these are all just multiple approaches to doing the same thing, right? To implementing a lock. Now, the store conditional only succeeds if no intermittent store to the address has taken place. So success indicates that we return a 1 and update the value at pointer to the value that we receive in this function. And fail means that the value at pointer is not updated and 0 is returned. Okay, so what are you talking about here? So this is slightly complicated, but load link here, right? It returns the current value of a memory location. Okay, and this will be like the current value of our lock, or our flag, indicating whether the lock is held or not. And the subsequent store conditional will store a new value only if no updates have occurred to this pointer. Okay, so if this function is called directly after load link without any other load link methods being called, then this will be true. Okay, so that's slightly confusing. So maybe if I go to the next slide, there's an example I can show you. So a better way of maybe thinking about this is, if say we have thread A running, right? Thread A does this, the lock is available, so this flag is equal to 0, and it called load link to determine that. So thread A called load link, and then thread B also then calls load linked. Okay, and then thread A calls store conditional. Now, because thread B had called load linked after thread A had called load linked, store conditional will basically fail. And that is what I'm trying to indicate here when I talk about this if statement. If no one has updated pointers since the load link to this address was called, so if no other thread has called load linked between myself calling load linked and myself calling store conditional, then I can return 1 indicating a success. If some other thread did basically update the pointer using load linked, then I'll return false. I know it's a little bit confusing, but if you go through it slowly, that's one way of understanding it. It's to ensure that multiple threads can't basically acquire the lock at the same time. This is just for basically some general knowledge. An easier way or more concise form of this type of lock using LLSC is just to have all of it rolled into a single conditional statement within the while loop like this. Cool. So moving on to another type of lock, and that is called fetch and add. So the idea here is that we atomically increment a value while returning the old value at a particular address. Now, this sounds very similar to what we had before, right? Where we return an old value, but we still update a value. And that's because it's very similar to fetch and store. So here we'll receive some pointer which is pointing to an integer variable, which is representative of our flag, which once again indicates if the lock is held or not. We'll say old is equal to that value, so say it's 0. We'll then say that our pointer is equal to old plus 1, which will be like 0 plus 1, and we return old. So we utilize this fetch and add approach for what we call ticket locks. And this basically ensures progress for all threads. So you remember when we had that spin lock, we had an issue with fairness. That one thread could be unlucky and basically starved of all CPU time. Well, our ticket lock basically is a solution to this. Now, it does involve a slight addition to our structure or our lock structure. And that is now we have our turn, a turn variable and a ticket variable, which replaced our flag variable. And once again, when we initialize everything, we're going to set ticket to 0 and turn to 0. Our unlock is basically going to, okay, I'll speak about that in a little bit, but I'll show you how it works. And our lock function is basically going to look like this now. So firstly, we get what my current thread's turn is, like the turn number. And we get that by calling our fetch and add with the ticket. Okay, so initially, say no threads had tried to acquire a lock. So initially, ticket and turn will both be 0. So my turn will equal fetch and add of basically 0. Okay, and if you remember fetch and add, we'll say old is equal to, and that would be 0. We then say point is equal to 0 plus 1, and return old, which will return basically 0. So my turn here would equal 0. And what is the current turn value? Well, the turn value is also 0. So this won't be true. So because 0 is not equal to 0 is false. So therefore I will exit my lock function and I've basically acquired the lock. But what else happened back then? Well, because we basically send in the pointer here, we're actually updating this pointer variable. And what is that? Oh, sorry. Well, that is lock ticket. So ticket was basically updated to 1 here. Okay, so that's something you got to be aware of. This pointer here, old was 1, basically updated lock tickets to 1. So now, if I then say unlock, I would say fetch and add lock turn. So I'll feed in 0. Okay. 0 will come in here. Old will be 0. And now we'll say pointer is equal to old plus 1, which will be 1. So turn will basically be updated with 1 now. Okay. Now, hypothetically, another thread comes along and says, I want to acquire the lock. Well, my turn will be fetch and add ticket. Okay. And this will basically return whatever the ticket value is, which will be 1. Okay. So my turn will equal 1. And it will also update this old variable, the pointer variable. So ticket will change to 2 here. So my turn will be equal 1. The current value of turn is also 1 because of the previous thread. And we'll say 1 is not equal to 1, which is false. So this will end and I will return. And then the unlock can occur again. But say hypothetically another thread wanted to acquire the lock at this time before, say, thread 2 finished the critical section. Well, what we have here is that we have ticket equaling 2, we have turn equaling 1. I will come into here, fetch and add ticket. This will return 2, and then update tickets to be 3. Lock turn not equal to my turn. So this is saying 1 is not equal to 2, which is true, so it will spin. And that's because the ticket is the lock is currently held. So that's how ticket locks work. Cool. So hardware-based spin locks are quite simple to implement, and they do work in terms of fairness and mutual exclusion, and performance is not too bad as well. However, in some cases these solutions can be inefficient. Now, anytime a thread gets caught spinning, it basically wastes an entire time slice doing nothing but checking a value. So how do we avoid spinning? How do we avoid spinning? Well, we'll need operating system support to do so. So we, in terms of like really efficient locks, need both hardware support as well as operating system support. Now, a simple approach would be just to yield. When you're going to spin, just give up the CPU to another thread. Now, the operating system call moves the caller from the running state to the ready state, and this is what we talked about in process abstraction as well as thread abstraction as well. Now, the cost of the context switch can be substantial, and the starvation problem may still exist. But how it changes things is, instead of just looping here, we just have the yield function. And this says basically, I'm gonna allowingly give the CPU up and just wait until a better time. So the real problem here is that our previous approaches leave too much to chance. The scheduler determines which thread runs next, and if the scheduler makes a bad choice, a thread might have to spin for a long time, and that was like our first approach, or they'll yield the CPU basically immediately, which was that second approach. Either way, there is a potential for a waste to occur, like a time efficiency or waste, and there's no prevention of starvation. To help alleviate this problem, we can use queues. And with queues, we can utilize sleeping instead of spinning. And there's a slight difference there. Now, we can utilize the queue to keep track of which threads are waiting to enter the lock. Okay. So basically, these would be the threads that would be spinning in our previous approaches. And we can utilize a park function, which basically puts a calling thread to sleep, and an unpark function, which basically does the opposite, which wakes a particular thread, as designated by whichever thread ID you feed it as an input. So this changes things up quite a bit. So now our lock structure has three components. It has the integer for the flag. It has this guard variable, but it also has a queue. Okay, and this is the general queues that you guys are all familiar with. And now our initiate function basically sets these variables to be 0 and initializes a queue to be empty. Okay, so that's how initialization of our lock changes. Now the lock function itself also changes up quite a bit. But once again, it utilizes test and set from before. Right? If you remember test and set, it would basically take in like a pointer to some integer variable. It would update that pointer with this new variable, and it would return that old variable. So if this variable was like 0, it would return 0 here, and it would update this guard variable to be 1 based on this condition here. So just the same as the test and set before. Okay, so what is this while loop actually here for? Like the other stuff I can kind of understand, you know, we acquire the lock here, we set the flag to 1 indicating we've acquired the lock, else we basically add ourselves to a queue and just sleep. So what is this while loop for? Well, it's to ensure that while some thread is trying to acquire the lock or release the lock, no other thread then starts the process of acquiring or releasing a lock. Okay, so we can just run through this together a little bit. Okay, so hypothetically, let's say that guard is equal to 0. Okay, what we're going to do is flag is 0, guard is 0. Right, we test and set, so this will return 0 because we give it 0. That's what test and set does, but it will update guard in the meantime as well. So guard will then be 1. Okay, this will say 0 is equal to 1, which is false, so it will continue going down here. So what you can see is we've set this guard variable to be 1 while we're basically doing the processing of these two conditions here. So we're basically like locking ourselves into here, or we're indicating to other threads that some thread is within this function, right? And if one thread is in this function, then we should just wait for them to finish. That's the idea. So say that so this is currently 1 because we're in here, and now another thread comes along and also wants to acquire a lock. Well, what happens is we say test and set of God, which will be 1. So this will return 1, and it'll update the value to be 1 plus 1, which will be 2. So God will now be equal to 2. So that indicates that there's currently 2 threads that are like within this region trying to acquire a lock. And this will say, well, 1 is equal to 1, which is true. So it will loop here, and it's basically waiting. So we haven't completely gotten rid of the wait, like the spinning. We're basically waiting here until some other thread has either acquired the lock or added themselves to the queue. So that's what's happening here. So this approach doesn't completely avoid spin waiting entirely. And that's because the thread might be interrupted while trying to acquire or release the lock. And in this case, threads need to spin and wait for one of those 2 occurrences to happen. However, it's still a lot better because the time spent spinning is quite limited, as you just have to wait for like a few instructions here to be executed, instead of waiting for an entire like user-defined critical section to be processed. And therefore this approach is fairly reasonable. So that's how locks with queues, test and set, yield, and wake up work. Actually, let me just show you the unlock. So the unlock also has the same guard approach. Okay. And basically, after that, we say if the queue is empty, we can then let go of the lock, meaning that no other threads are wanting the lock, so we set the flag back to 0. Else, if the queue isn't empty, we then going to say, we then going to basically hold the lock, indicating that another thread is going to utilize it, and we're going to set guard to equal 0, so that one of those threads that are currently waiting within that lock function, within this like guard while loop, will therefore be able to access the rest of the function. Because if we in the unlock set guards back to 0, one of these guys will be able to get out of this while loop and therefore continue down here. Cool. So that's how we utilize this approach with queues. There is, however, one additional thing that needs to be considered, and that's the case of, say we're releasing a lock, or thread A is releasing a lock, and they release the lock just before thread B calls park. This would mean that a thread B would sleep forever. So the idea here is that thread B is just about to call park, meaning that they're going to wait for for an unlock to occur. But just before that happens, thread A actually unlocks. Now that results in thread B basically sleeping forever. So a slight modification to the code is this set park function. So Solaris solves this problem by adding a third system called set park. And by calling this routine, a thread can indicate it is about to park. And if it happens to be interrupted and another thread calls unpark before park is actually called, the subsequent park returns immediately instead of sleeping. So this is just one way to get around this wake up / waiting race. So it's just a slight code modification where you just call this function before whenever you actually call the park function. Cool. So similar to Solaris, Linux provides its own similar like park and unpark functions, and these are futex wait and futex wake. And they basically do the same thing, so I'm not going to get into it too much. And here you can look at the code for it. It's a little bit complicated, but just the key takeaways is that they utilize 32-bit integers. So they say that the 31st bit, which is like that 30-second value, because we're starting at 0, indicates whether our integer is positive or negative. And this disparity between positive and negative is what they use to track whether the lock is held or not. So if the integer is negative, you can hypothetically think of the lock as held, and if it's positive, then the lock isn't held. And the other bits are used to indicate the number of like threads that are in the queue, hypothetically. So in other words, firstly, it uses a single integer to track both whether the lock is held or not and the number of waiters on the lock. So whereas before we had like a flag and a queue, now we can just roll that up into a single integer, which is very efficient. Thus, like I said, if the lock is negative, it is held because the high bit is set and that bit determines the sign of the integer. And on top of that, our code snippet here shows us how to optimize for the common case where there is no contention for the lock. And that is this if statement here. So if there's no contention for the lock, we just return instantly. Otherwise, we'll do all this additional work. So that's quite efficient in terms of processing time. So that's all I really want you to get out of this Futex stuff, is that there's a couple different like optimization approaches that they've utilized and clever usages of data types like integers. But nothing, you don't have to really understand it in too much detail. Cool. So the last lock that we're going to be looking at is two-phase locks. And our two-phase locks realizes that spinning can be useful if the lock is about to be released. Okay, so the idea here is that in some first phase, the lock spins for a while. So you know when we had all these while loops, that's what I mean by spins. And it spins for a period of time hoping that it can acquire the lock. If the lock is not acquired during this first spin phase, and this will just be like a set amount of time. So if it is not acquired during this first spin phase, a second phase is entered. Okay. And within the second phase, so this will be like another, like an if statement basically. So if we've exited the first phase and fallen into the second phase, the caller is put to sleep. So the thread that called this lock function will be put to sleep, and it will only be woken up when the lock becomes free later. So here we're basically trying to game the system a little bit, in the sense that we're going to assume that we can acquire the lock fairly quickly. So we'll just spin, wait a little bit. If not, then we'll be put to sleep. So that's the idea of two-phase locks. And that is basically going to be the end of this lecture on locks. I hope everything makes relative sense. And it's just lots of different ways of implementing the same basic idea, right? Of we want one thread to have the lock and all the other threads to basically be waiting their turn. And once the thread that had the lock has finished its critical region, then we want that thread to release the lock so that another thread can obtain it. In next week's lecture, we're going to be looking at a different approach instead of locks to our synchronization. So once again, thank you very much for listening, and I'll see you next week.